Alright, so we're going to introduce another new concept that again isn't really new. So we're going to start talking about magnetic flux, and magnetic flux will be important in terms of the idea of thinking about electromagnetic induction. But magnetic flux works exactly the same way that electric flux did. So if you remember when we talked about electric flux, we said it's a measure of how much an electric field flows through a particular surface. And we said that it depended on three things. One was the strength of the electric field, two was the area of the surface, and three was the relative orientation of the electric field in the surface. So if you could increase the electric flux by making your field stronger, that would be more field lines. You could increase your electric flux by making your area bigger, that'd be more field lines. And you increase the electric flux by lining up your electric field and the area vector for your surface. So in this case, they're oriented to get the maximum amount of flux. Now, if you wanted to calculate the electric flux, in general, again, it's a double integral of E dot dA. So you're thinking about the projection of the electric field onto all your little area elements, and then you're adding all those up over the two dimensions that you've got involved in your area. More commonly, we said if we have a constant electric field over a flat surface, then what we end up doing is we end up simplifying this, and so this integral simplifies into the magnitude of the electric field times the magnitude of the area vector times the cosine of the angle between those two. So we remember that the area vector is normal to the surface itself. So if the surface is running like this, you can see that the area vector is perpendicular to that surface. And so theta here in this particular equation happens to be the angle between the electric field vector and the area vector. So in just an absolutely analogous way, magnetic flux is a measure of how much a magnetic field flows through a particular surface. And again, the magnetic flux depends on three things. It depends on the strength of the magnetic field, it depends on the area of the surface, and it depends on the relative orientation of the magnetic field in the surface. So again, if you wanted to increase the magnetic flux, you could increase the magnetic field. That would give you more field lines coming through your surface. You could increase the area of your surface, so instead of being L on each side, you could make it 2L or anything bigger. And you can increase the flux by lining up the magnetic field with the area vector for your surface. So you notice here, the area vector is not aligned with the magnetic field. So we're not getting the maximum value of magnetic flux that we can. If you wanted to get the maximum value of the magnetic flux, you would need to tilt your surface so that it's running perpendicular, so that your surface is perpendicular to the magnetic field, which means that your area vector would be aligned with the magnetic field. Again, in terms of calculating this, well, all we've done is basically replace the electric field with the magnetic field. And again, this is just a double integral over a bunch of little area elements where what I'm interested in is the projection of the magnetic field onto each area element, and then I'm just going to sum it up over the two dimensions that I need to integrate over. If you have a constant magnetic field over a flat surface, then once again this integral simplifies, and so this becomes magnitude of the magnetic field, magnitude of the area vector, cosine of the angle between the magnetic field vector and the area vector. So again, that area vector being normal to the area itself. So this is basically exactly the same. Magnetic flux is exactly the same as the electric flux. It's just interested in how much the magnetic field flows through your surface rather than how much the electric field flows through your surface. Well, just like we said, again, that dot product cares about the relative orientation. So the electric flux was at a maximum when the surface is perpendicular to the direction of the electric field, which means the normal to the surface, or the area vector, is parallel to the electric field. Same thing's true for the magnetic flux. It's at a maximum when the surface is perpendicular to the direction of the magnetic field. Again, if your surface is perpendicular to the magnetic field, that means the area vector, which is normal to the surface, is parallel to the magnetic field. So again, the relative orientation matters in terms of thinking about either of these fluxes, either the magnetic or the electric flux. So in terms of units, well, you can see that this is just going to be thinking about our simplified equation. Well, the units of magnetic field are Teslas. The units of area are meters squared. Cosine theta doesn't have any units, it's just a number. So the units of magnetic flux are Tesla meters squared, but that gets called a Weber. So we will refer to the units of magnetic flux in terms of Webers. And the important thing, the reason we're going to care about magnetic flux, we said we cared about electric flux because of Gauss's law and what we learned that the electric flux was proportional to. We're going to care about the magnetic flux because when you change the magnetic flux through some loop, you induce an electromotive force which induces a current around the loop. So let's start by talking about electromotive force. We've seen this symbol before, right, using this lowercase epsilon. And really what this is, the electromotive force is not a force. It's again, one of these old labels that we've carried on for many years that's probably not in anyone's interest, because the electromotive force is not a force. What it is it is a voltage. So now we have yet another way to talk about the potential difference. So talking about the potential difference, the voltage, the EMF, those are all the same thing. And so sort of the more common way that we would read this in terms of language is that when you change the magnetic flux through some loop, it's going to induce a voltage, induce a potential difference, which then induces a current. Right? So that potential difference that's created by changing the magnetic flux will end up driving a current around your loop, assuming that your loop is conducting. So what this means is, just thinking about this equation up here, there are three ways to change the magnetic flux through a loop. So there are three ways to change the flux, because you can either change the magnetic field, or you can change the area of the loop, or you can change the relative orientation between those two things. So what we will concentrate on going forward when we start talking about electromagnetic induction is we need to have a really good grip on the magnetic flux so that we can figure out which of these three parameters we're changing to think about how we're inducing current around some loop simply by changing the magnetic flux.